Okay, so today's speaker is Vikram Rentala from IIT Bombay. So Vikram did his PhD at University of Berkeley with Hitoshi Murayama, and afterwards he had several postdocs at Arizona, Michigan State University, and Carleton University. And in 2014, he became a faculty at JNU University, and since 2015 he is at IIT Bombay. So he started off in collider physics, but he's now working more in the direction of astroparticle physics, and today he will be talking about broadband 21 centimeter cosmological signal from dark matter spin flip interactions. So please begin.
Okay, thank you very much, Michael, and thank you for the kind invitation to give this talk. So I'm really excited to talk about this recent work that I did with my collaborators on broadband 21 centimeter cosmological signals from dark matter spin flip interactions. This should appear in JCAP in about a week or so. Okay, so let me just, can you see my cursor on the screen?
Yep.
Okay. Okay, so so let me just tell you sort of a brief history of the universe, and I'll tell you what, and this history of the universe, I'll connect it to what this 21 centimeter cosmological signal is. So this is the history of the universe from the Big Bang till today, and this is time, and today the universe is about 13.9 billion years old, and somewhere about 400,000 years after the Big Bang, okay, the universe transitioned from a universe which was fully ionized to a neutral universe. So the hydrogen, you had recombination where electrons combined with protons into neutral hydrogen. And so before this, the universe was ionized. And at this point is where the cosmic microwave background was emitted. And meanwhile, the rest of the matter, which was not in the form of photons, which is dark matter and the baryons, they continue to evolve quietly under gravitational influence, and dark matter eventually formed clumps and baryons fell into those clumps, and eventually at some later time, about 150 million years after the Big Bang, they started to form the first galaxies. Okay, and these first galaxies, the first stars that were created started creating these ionizing radiation or ionizing bubbles around them. And once again, eventually, once enough galaxies had formed that you created enough ionizing bubbles, the gas in the universe, all the baryons which were now in the form of neutral hydrogen, turned into ionized radiation. So this is expected to have completed something like 1 to 2 billion years after the Big Bang, is the universe again transitioned from a state of complete ionization to neutral to again being completely ionized. Okay, meanwhile, the galaxies continue to coalesce, and today we see the distribution of galaxies in the large-scale structure of the universe. So cosmologically, this entire story is known to us because of two fantastic probes that we have of the universe. One is the distribution of galaxies that we see today, okay, in the large-scale structure. And another picture that we have of the universe, or a snapshot that we have, is at very early times at recombination when we observe the cosmic microwave background. So it's sort of like if we look at this story of the universe, we have a picture of the universe as a baby when we see it at recombination. And we have a picture of the universe as an adult, okay, that is today. But very soon, we are going to have a picture of these turbulent adolescent years, okay, of the universe, through the period where the universe went through these dark ages and reionization. So we have a sort of a story which hangs together, which tells us how recombination connects to the present day structure that we see in the universe, but we don't have direct experimental observations of this intermediate epoch. Now, the reason why we don't have direct experimental evidence of what went on in this epoch is easy to understand. It's only once the galaxies started lighting up that you actually have sources that you can see. Okay, so you actually only start having sources around a redshift of 10 or later. Okay, so the furthest objects that we've detected are maybe redshift 7 or 8. Okay, it's really hard to see anything beyond that. And moreover, in the dark ages, when the hydrogen is neutral and when star formation hasn't started yet, there is almost nothing that's emitting radiation that you can detect. Okay, But as I'll talk about, neutral hydrogen actually has a particular transition called the 21 centimeter hyperfine transition. And observation of this 21 centimeter signal is a tracer of neutral hydrogen. Okay, so you can actually use it to probe not just the dark ages, but you can also probe the epoch of formation of the first stars and galaxies, which is going to be very exciting in the near future. Okay, maybe on a time scale of a few years to 10 years. Okay. So let me talk about the predicted global 21 centimeter signal that we expect to see in the standard cosmology. Okay, so over here is the frequency of the signal that you would measure. And this frequency of the signal is a 21 centimeter signal, but it's emitted at, or it corresponds to a particular redshift, okay? So this is redshift, so redshift of 10. So if you go back to this previous slide, a redshift of 10 corresponds to here around the epoch of reionization, and a redshift of 1000 is recombination, okay? So this is looking at relatively low redshifts compared to recombination. This is only going up to a redshift of about 160 or so. And what you have on the y-axis is some kind of measure of intensity of this 21 centimeter radiation. Okay, so I'll tell you what this measure of intensity is at some later point. But the key thing to note is that you have these two absorption dips, okay, that you see. And these absorption dips, one of them is occurring deep in the cosmic dark ages. That is this era here, where you just have neutral hydrogen. And a second dip that you expect to see is around the time the first sources turn on, that is when star formation first began. And some models also predict an emission signal that you should see. And once reionization ends, that is once the universe no longer has any neutral hydrogen, you expect this 21 centimeter signal to disappear. Okay, so there are many experiments looking for this exciting signal, and especially this epoch, somewhere around a redshift of 20, which corresponds to frequencies in the range of 60 to 100 megahertz. This is really interesting because it's going to tell us about the formation of the first stars and first ionizing sources, which include active galactic nuclei or X-ray sources. Okay, so there are many experiments looking for this 21 centimeter signal, and you can see that this corresponds to your similar to your FM radio frequencies at hundreds of megahertz. So there's the global signal. This is called the global signal because this is the isotropic signal that you measure in the sky. You could also see, if you look at different parts of the sky, so this is, let's say, one angular patch of the sky, and this is a particular redshift, you will see different signals at different angular patches. So that is called the anisotropic signal. We're not looking at that. We're looking at the averaged signal across different angles. And that is what is called the global signal, which is shown in this plot. Okay. So there are many signals many experiments which are looking for this global signal. One of the more famous ones recently is the EDGES experiment, but there are many others as well, which will go up to a redshift of 15 and will probably probe the formation of these first sources. Going deeper into the cosmic dark ages, up to a redshift of 46 to 80 would be these experiments, LIDA and DAPA. And to really go very deep into the cosmic dark ages and to see something all the way up to maybe a redshift of 1000, you need space-based experiments, which are shielded from radio noise on the Earth. Like these far side, Pratyush is an Indian effort, and there is the Netherlands China Lunar Explorer. These might probe all the way up to a redshift of 1000 or so. Okay, so this is the EDGES experiment, and in 2018, they claimed the discovery of, or they claimed something like a discovery of this signal. So they probed a range of something like 60 to 80 megahertz, and they claimed that there was a signal in there. So in this range of 50 to 100 megahertz. Now, the thing is that the signal that you're looking for is actually hidden under cosmological foreground. So there's also 21 centimeter emission from or absorption from our own galaxy. And that signal looks something like this. Okay, so it's not 21 centimeter, it's just emission at these frequencies. Okay. And so it's measured in terms of some intensity, and that scale in temperature is in Kelvin, and it runs in thousands of Kelvin. The signal that you're looking for and the signal that they claim exists in here, okay, is some very small dip over here, which is of the order of 0.5 Kelvin, okay, or 500 millikelvin. So they claim that on top, hidden under this thousands of Kelvin variation, okay, in this signal, they can dig out this small signal which has an absorption dip of minus 0.5 Kelvin. Okay, so this was really exciting because it seems to be roughly in the right location that you expect the first sources to have turned on. So it was really exciting because this is a first signal, cosmological signal of that epoch. However, subsequently, people raised a lot of issues about the modeling of maybe the foregrounds that give rise to this emission and how those foregrounds could possibly mimic such a signal, or maybe it could have been some kind of instrumental effect. And so a lot of people doubt whether now the signal is really cosmological. So maybe we have not yet really understood how to extract the 21 centimeter signal, okay, from this kind of observation. However, in the future, many of these experiments may have the potential to discover a 21 centimeter signal. So our motivation was, are there any other classes of predicted 21 centimeter signals in beyond standard models of particle physics that could be tested by these future experiments? Okay, so are there models which, so given that there is a large uncertainty, even from astrophysics, okay, so we don't quite know where this absorption dip should occur. We don't quite know its exact magnitude. Okay, so to give you an idea of how much variation there can be, this absorption dip could be anywhere between 50 megahertz to 110 megahertz, okay, depending on what you assume are the properties of the first sources and so on. There is about 100 millikelvin uncertainty in the absorption dip itself, okay, the magnitude of this absorption dip. One of the interesting things seen by EDGES was that the typical magnitude of this absorption dip is expected to be about 100 to 200 millikelvin. But what EDGES saw was an absorption dip of almost 500 millikelvin, okay, which is much stronger than what was expected from any astrophysical model of what that absorption dip was. So this was already exciting from the perspective that maybe there's already some beyond standard model physics that is needed to explain this, this absorption dip, because standard astrophysics doesn't seem to explain it. And so there's a lot of discussion of beyond standard model models. But even if you don't take the EDGES signal seriously, okay, the question is, are there other things that maybe we have not thought of looking for that could have an imprint on the 21 centimeter signal? And even given the fact that you have all this astrophysical uncertainty, maybe these signals might just stand out as something completely unexpected, okay, which you could test with these experiments. Okay, so this first absorption dip over here is much more robust. Okay, so the first absorption dip is much more robust. We have a pretty good understanding of where exactly the minimum of this dip should be, what its shape should be, and also how strong this absorption dip is. Okay, so predictions that you make down here can be more robustly tested in the sense that it's very hard to mimic any new prediction in this region with standard astrophysics. Okay, so let me just give you a preview of our key result, and then I'll talk about how we actually get to this result. Okay, so this is that same absorption dip. Okay, again measured as some measure of intensity as a function of frequency. This red signal is what you'd expect in some standard cosmological model. Okay, so you have two absorption dips, and these are relatively weak absorption dips. But one key feature is that you have two distinct absorption dips, one in the cosmic dark ages, and a second at some higher frequencies, which corresponds to star formation. Okay. Now, what EDGES saw was in this narrow band of frequencies, and that is this gray absorption dip, which is much stronger than what is expected in standard cosmology. So this goes down to something like minus 500 millikelvin. So you have beyond standard models which already exist, which provide something called excess cooling of the hydrogen gas. So they allow it to cool significantly. And those models predict an absorption dip which seems to match that, or can roughly match the magnitude of the absorption dip seen by EDGES, although not quite the shape seen by EDGES. Okay, what we're after is a different model, which makes this different prediction, okay, which makes a prediction of a much stronger absorption dip, and is also much more broadband. It's spread across a wide range of frequencies, as opposed to having these sort of narrow band or band limited features, okay, which exist only in a certain range of frequencies and then disappear, okay. So this is sort of our prediction, which could be tested by these upcoming experiments. Okay, so in contrast with the standard cosmology or even these excess cooling models, which have been designed to explain the edges signal, we do not predict two distinct band limited absorption features. Rather, we predict one single broadband absorption feature, and some of these and this feature exists sometimes in regions where we do not expect any signal at all in cosmology, where we do not expect any negative absorption dip. That is, where this blue curve dips is the signal, right? And you see that there are certain regions where you do not expect a signal at all cosmologically in the standard cosmology. The absorption signal in the standard cosmology is typically fairly weak, okay, even for the edges signal, okay, to get the strong, okay, you can get a second absorption dip, which is strong, but the first absorption dip is still weak, even in the excess gas cooling models, okay, and another important point, which I'll discuss later, is that the spin temperature, which I'll discuss what that means, traces what is called the gas kinetic temperature, that is the thermal motion of the hydrogen atoms. But that is not true in our model. In fact, this measurement of this would tell us something about the thermal energy of the dark matter particles rather than about the temperature of the hydrogen gas. Okay, so that's another interesting feature about our model. So here's the basic idea of what the model is. It's really simple. It's dark matter interacting with electrons through an axial vector mediator. And what this interaction does is it flips the spin of an electron inside neutral hydrogen. So this electron could be inside neutral hydrogen. And the interaction would flip the spin of the electron. Okay, so if you have an up-type spin, which is aligned with the spin of the proton, it would flip it to a down-type spin of the electron, which is anti-aligned with the spin of the proton. Okay, so this is just a simple model. And just a simple model in some regions of parameter space could lead to an absorption signal this strong. Okay, and the other important point that we've shown in this work is that this model is surprisingly safe from constraints, in that you can actually get a very strong absorption signal. Okay, so there are several other people who have also tried to talk about spin flip interactions, but those are mostly in the context of trying to explain the edges signal. Okay, that's not the focus of our work, and moreover, we find that it's unlikely that you'll explain a narrow band feature with the spin flip interactions. Rather, what we've generically shown in our work is that you will get broadband absorption signals if you have spin flip interactions. Okay, so this is the big picture idea of what we've done, and now what I'm going to do is I'm actually going to tell you about the specific aspects of our work. Okay, so to do this, sorry, before I go ahead, let me just acknowledge my collaborators, Mansi Durya, who's now faculty at IIT RAM in Ahmedabad, Priyanka Sarma, who's a graduate student at IIT Bombay and who is graduating this year. And there's Viraj Karambelkar, who's a former undergraduate student and who's now at Caltech. Okay, so here is a quick outline of my talk. So what I'm going to do is first I'm going to talk about the standard cosmological 21 centimeter signal, because it's important to understand how that signal arises if we want to understand how dark matter interactions could modify that signal. And I'll also talk about how these excess cooling models differ from the standard cosmology. And then I'll also tell you how our spin flip interaction model differs even further, goes one step further than just these excess cooling models. Then I'll talk about the global 21 centimeter signal in our dark matter spin flip model, and finally some constraints on our model, and I'll show you how our model is safe from these constraints. And then I'll talk about future directions and other alternative probes that you could use to test our model. Okay, So I'll spend roughly half the time that I have on talking about the standard cosmological signal before I get to the dark matter spin flip interaction. Okay, so the 21 centimeter global signal in the standard cosmology is something like this. Okay, so let's first talk about neutral hydrogen. So neutral hydrogen has a proton with an electron going around, and the proton and electron both have spins. And these spins can couple into a singlet state, or they can couple into a triplet state. By the way, sorry, if there are any questions, please feel free to ask me in the middle. I'm happy to pause for questions. Since I assume the physics of 21 centimeters is probably not familiar to everyone in the audience, so I'm happy to pause at any time. Okay, so these spins can align into either a singlet state or a triplet state, and the well-known hyperfine splitting of the hydrogen atom leads to the energy levels of the triplet being slightly higher than the energy levels of the singlet. Okay, so the energy level of the singlet and the triplet are split by an energy which is about 6 microelectron volts, and this corresponds to so if you have a de-excitation from the triplet to the singlet, that would lead to an emission of a photon with a wavelength of 21 centimeter, or equivalently a frequency of 1420 megahertz. Okay, and if you write this energy scale in terms of a temperature scale in unit, by putting in a factor of the Boltzmann constant, you get a temperature which is 69 millikelvin. Okay, so this is a very small energy splitting indeed. Okay, and you can ask, what is the natural lifetime for an electron in the triplet state to decay down into the singlet state? And that lifetime, if you naively estimate it, you would say it's some alpha, where alpha is the fine structure constant, times the splitting, which is delta. But it turns out that this transition is even smaller, because this is a highly forbidden transition. So it's actually suppressed even further by delta over me square. It turns out that therefore this is the decay width, and therefore the lifetime is very large. The lifetime turns out to be 10 million years. Okay, so spontaneously, if you have a hydrogen atom in the triplet state, it will not decay to the singlet state over a time of 10 million. It will take 10 million years to decay down to the singlet state. Okay, so over this time scale, okay, you can think of the population as being as sort of not changing or over shorter time scales. There is no equilibrium which you can establish, right, between these two. However, what you can do is, whatever the population of the triplet state, which I'll call the 1 state, so that's N1, and the population in the ground state, which is the singlet state, which we'll call N0, that ratio can be parameterized as if it was a thermal population. So you write it as 3, which is the degeneracy of the triplet, times an exponential of minus the splitting over some parameter Ts, which is kind of plays the role of a temperature. Okay, in the sense, if this was a thermal population, you would say Ts gives you the temperature of this population. Okay, but really you should think of Ts as some way to parameterize the number in the excited state versus the number in the ground state. Okay, so Ts is just this parameter that describes the relative population of singlet and triplet states. And since delta is so small, okay, the typical spin temperatures that we'll be looking at are large, and therefore roughly you have equipartitioning, in the sense that you have equal probability of being in any one of these 4 states. So N1 by N0 is approximately 3. Okay, so when you're talking about Ts not being infinite, but really some finite value, but large, you're talking about deviations from equipartition. Okay, that is how much does this population differ from each state being equally probable for being populated. Okay, and that deviation is very, very small. Okay, as we're going to see, but that's the deviation that we're interested in measuring. How different is it from equipartition? Okay, this temperature is not to be confused with the kinetic temperature of the gas. The kinetic temperature of the gas is due to the kinetic energy of the entire hydrogen atom. Okay, and so this Ts is not necessarily the same as this kinetic temperature of the gas. Okay, so the spin temperature is very important because it tells us what the relative populations are of the triplet and singlet states, and this relative population will control the amount of 21 centimeter radiation that we see. Okay, so let's go back to that picture, that cosmological picture. Okay, so I told you that we'll have photons from recombination that we see today. And those photons that we see are the Cmb photons. Okay, so the Cmb photons have a black body spectrum with a temperature of 2.7 Kelvin. And this is their intensity as a function of frequency. Now, the Cmb photons, so we've measured this black body spectrum extremely well over a large range of frequencies. And this 1420 megahertz, which is 1.4 gigahertz, or equivalently 21 centimeters, that 21 centimeter photons would be here. Okay, but these are 21 centimeter photons today. What we're interested in is a photon that was a 21 centimeter photon at some earlier epoch, okay, at some redshift Z, okay? And we're interested in asking, so you have these Cmb photons, which are black body photons, which reach us with some frequency spectrum today, but we're not interested in these photons. Rather, we're interested in the photons that were 21 centimeter photons, okay, at some redshift Z. Okay, now down here, okay, this region of the black body spectrum is called the Rayleigh-Jeans tail, and down here, the black body law it's much more simple to express. The intensity as a function of frequency just grows as the frequency square, and it's proportional to the temperature of the black body. Okay. Now, if we're interested in photons which were 21 centimeter photons at some earlier time, today they must be much longer wavelength photons because they're redshifted. So they would actually be much, much, much further down over here. Okay. So for example, something from a redshift of 10 would be at 0.1 gigahertz. Okay. So that's somewhere down here. So, and if you're looking further back in redshift, you're looking further away. And down here, we don't quite know if the spectrum is a black body or not. Okay. So the frequency that we measure, if we're interested in a photon that was 21 centimeters or 1420 megahertz at a redshift Z, the frequency that we measure today would be much lower frequencies, okay, because it's redshifted. So we're interested in what is the intensity of those photons, which were 21 centimeter photons at a redshift Z, or which have a frequency nu today. And again, if they're black bodies, okay, they would have this intensity. However, if they're not black bodies, we would measure some different intensity, and whatever that intensity is, we can pretend that the law is black body like and try to figure out what the temperature is that corresponds to those photons. Okay, so for every frequency, we can define a temperature, and that temperature is called the brightness temperature. So that is the would-be black body temperature of the photons that we see down here. Okay, and what we want to do is we want to compare that would-be black body temperature to the actual black body temperature of the photons, okay, of the Cmb photons, okay. And that difference between the would-be black body temperature and the actual black body temperature of the Cmb photons is a measure of the difference between the intensity of those photons at some frequency and the intensity of the Cmb photons, okay. So what you're really measuring is some measure of net absorption or emission of these 21 centimeter photons. So these 21 centimeter photons are actually coming from the Cmb, and these are for some kind of backlight. Okay, so it's like someone is shining a torch or a flashlight from some earlier epoch, and this light passes through some medium, and you're trying to measure if this medium is going to emit some extra 21 centimeter radiation, which would be an emission signal, or it's absorbing some 21 centimeter signal. Okay, and how you measure that is you measure what is called the differential brightness temperature, which is a measure of the intensity that you actually measure at some particular frequency minus what you expect from the Cmb at those frequencies. And it should not be surprising, okay, that the difference between these two, okay, or what you actually measure, is proportional to two things. One is it's proportional to the amount of neutral hydrogen that you have. Because if you don't have neutral hydrogen, then it's only neutral hydrogen that's absorbing or emitting these 21 centimeter photons in any significant amount. So it has to be proportional to the amount of neutral hydrogen. So this XHIZ is the fraction of hydrogen at that redshift, which is in the form of neutral hydrogen, okay, as opposed to ionized hydrogen. And what you have over here is the difference between what is called the spin temperature, that is how much of hydrogen is in the excited state versus how much is in the ground state. It's some measure of that compared to the Cmb temperature. Okay, so it's the difference between the spin temperature and the CMB temperature. And if you can see that if the spin temperature is the same as the CMB temperature, then in some sense, you can think of the spin occupation as being in equilibrium with the CMB, and therefore you do not expect any net emission or absorption. Okay, so that's why it's proportional to Ts minus TCMB. When the spin temperature is exactly equal to the CMB temperature, there's no net absorption or emission. But when the spin temperature is lower than the CMB temperature, that means you have more hydrogen in the ground state, and therefore you will have net absorption. Okay, and delta TB would be negative in that case, so you have a net absorption signal. If delta TB is positive, that means the spin temperature is larger than the CMB temperature. You have more hydrogen in the excited state, and that's leading to net emission. Okay. Okay, so the signal that we saw, okay, this brightness signal as a function of frequency looked something like this. There were two absorption dips where the brightness temperature went negative. And then the first was in the cosmic dark ages. The second was when the first source is turned on. And then I told you that some astrophysical models predict also an emission signal, okay, which is basically saying that the spin temperature is now larger than the CMB temperature. And eventually reionization ends, but the reason reionization ends and then the hydrogen fraction actually goes to zero. So through this entire epoch, mostly this hydrogen fraction is mostly in the form of neutral hydrogen. And so this is just 1. And somewhere here, this prefactor makes a transition from 1 to 0 because there's no more neutral hydrogen and your emission signal ends. Okay, so now what we're going to try to understand is if we want to understand this profile of this absorption signal, what we need to understand is how the spin temperature varies with redshift. Okay, that is how the population of the excited states and the ground states varies with redshift. That will tell us how the spin temperature varies with redshift. And once we know how the spin temperature changes with redshift, we understand why we expect to see this kind of absorption signal and this emission signal. And of course, we expect the end of this because reionization takes place. Okay, but understanding the behavior of this signal really requires us to understand how the different hyperfine states of hydrogen are populated and what are the mechanisms that drive that population. Okay, maybe I can pause for a few questions at this point.
So just to understand, so basically the so delta TB was negative for what H is measured.
Yeah.
So it basically was going down much more than what was expected. So that's always technically, but in some sense goes in the same direction as the brightness.
Right. So basically, if what that means is Ts of Z is what edges has seen is even deeper, right? Which means that the spin temperature is even smaller than what you expect. Okay, which means that you have more hydrogen in the ground state, right? And that's why you have more absorption, right? So you have more hydrogen in the ground state than you actually expect. Okay, so if you want to explain the edges signal, you have to explain why there is more hydrogen in the ground state. Okay, then what you expect in the standard cosmology. Okay, so standard cosmology also you expect more hydrogen in the ground state. I mean, you expect this deviation from equipartition, where there is slightly more hydrogen in the ground state than in the excited states, as compared to the equipartition expectation. But there's a limit to how much you can be in the ground state. Okay, and what edges seem to indicate is that you should have a lot more hydrogen in the ground state. Okay, so let me talk about the mechanisms that control the spin temperature or the population of hydrogen in the ground state and excited states. Okay, so there are 3 main mechanisms, okay, in the standard cosmology that can alter the population between the excited and ground states. There are CMB excitations and de-excitations. So each of these has a rate coefficient, which I've written over here. So B01 is the rate for excitation of a hydrogen atom from the ground state to the excited state by absorption of a CMB photon. A10 is the decay lifetime for, or the inverse decay lifetime, which is the decay width for spontaneous emission. That is, for something in the excited state to drop down to the ground state, and that would emit a photon. And you can also have stimulated emission. That is, CMB photon comes in, causes de-excitation, and also, and in the process of de-excitation, you emit another 21 centimeter photon. So you have all these three processes, which can lead to either absorption or emission of 21 centimeter photons. But more importantly, they change the occupation numbers of the hydrogen between the excited and ground states. Okay, and so this really controls what will be what the relative populations will be in the excited and ground states. But in addition to this, you also have collisions between the hydrogen atoms. And so the hydrogen atom could collide either with another neutral hydrogen atom, or it could collide with ions. But in either case, that collision itself could cause an excitation or a de-excitation. And so these collisional rates are written here as C01 and C10. C01 is the excitation rate from the ground state to the excited state. C10 is the de-excitation rate. So all these rates have units of inverse time. So this A10 is that time that I already told you about. It's 1 over 10 million years. Okay. This is the spontaneous emission rate. Okay, and you can work out what these other rates are, and these other rates. The important point is these other rates would depend on temperature. Okay, then you can also have, once the first stars turn on. I told you that transition, the hyperfine transition, is forbidden. But what you can have is you can have absorption of a Lyman-alpha photon, and the stars emit copious amounts of Lyman-alpha photons. And this could cause an excitation to a higher state, like a 2p state. And you can have a de-excitation from the 2p state down to the lower hyperfine state. So you could have these kind of transitions. And these are not forbidden. Okay. So now you have Lyman-alpha photon excitations and then de-excitation. So this is called the Otysin field effect. And there are some rate coefficients for this as well. Okay. But these processes become important only once star formation turns on. But you can see that all these three processes would sort of drive the population of hydrogen between the ground states and the excited states. Okay. Now, for want of time, I won't go into all the details of how exactly they drive these. But one important point that I will make is the final expression that you get for the spin temperature is that the spin temperature is related to all these rates. Okay, the final spin temperature is related to all these rates. And each rate is trying to couple the spin temperature to a different temperature. So the first set of rates are trying to couple the spin temperature to the CMB temperature. Okay, so they're trying to drive the spin temperature, or the population of these two, into equilibrium with the CMB temperature. This set of rates, okay, which is collisional rates, are trying to drive the spin temperature into equilibrium with the kinetic temperature of the gas, that is the thermal energy of the gas particles. Okay, and the gas itself is not necessarily in kinetic equilibrium with the CMB. Okay, and this other set of rates, which are rates from the first star, first induced due to the first stars, this is trying to drive the spin temperature into equilibrium with yet another temperature scale, which we call the color temperature, or TC. Okay, and for all practical purposes, we can assume that temperature is, let's say, the same as the gas collisional temperature. Okay, so the spin temperature can couple to three different temperatures. It can couple to the CMB temperature, it can couple to the kinetic temperature of the gas, or it can couple to the color temperature. And which one it couples to is determined by the size of these effective coupling constants, okay, which we'll call XC and X alpha. This XC is a measure of the collisional rate to the CMB rate. This X alpha is a measure of the Lyman-alpha rate to the CMB rate. So whenever one of these couplings is large, okay, so if XC is very large, then the spin temperature is coupled directly to the kinetic temperature of the gas. If X alpha is very large, then the spin temperature is directly coupled to the color temperature of the gas. And if both of these are small, then it's that is the B10, that is the CMB induced rate is the largest. Then the spin temperature is coupled to the CMB temperature. Okay, so again, I'm going to ignore the difference between the color temperature and the kinetic temperature. So there are two possible scales that you can couple to. You can either couple to the CMB temperature, or you can couple to the kinetic temperature of the gas. Okay, so I'm going to skip a lot of this and just come directly to how. So to understand now the spin temperature, okay, because the spin temperature tells us what the absorption signal will be. To understand the spin temperature, we need to understand how the CMB temperature changes with redshift and how the kinetic temperature of the gas changes with redshift. And we also need to understand how these rates evolve with redshift. That is this coupling rate XC and X alpha, how those change with redshift. Okay. And those have to do with these collisional rates, collisional induced spin flip rates, and the CMB induced spin flip rate. Okay, so I won't go into the details, but let me tell you what the result is. So this is in the standard cosmology. So this is not our work. So initially the kinetic temperature of the gas, so this is as a function of redshift. This is high redshift, which is early universe. This is low redshift, which is late universe. Initially, the gas is actually kinetically coupled to the CMB. So even after recombination, when the electrons combine with protons, you still have a few residual electrons. So the universe never is completely neutral. There's a small amount of residual ionization. Okay, and those residual electrons still interact kinetically with the CMB, and they can cause the gas. They also collide with the gas, the neutral hydrogen, and they keep the gas at the same temperature as the CMB. So at very high redshifts, okay, somewhere between a redshift of 150 and 1000, the gas and the CMB are still in kinetic equilibrium. Okay, even though they're no longer in chemical equilibrium. Okay, so they maintain kinetic equilibrium. However, around a redshift of 150, okay, there is this electron coupling to the CMB becomes inefficient at keeping the gas in equilibrium with the CMB. So the gas begins to cool kinetically. Okay, so now it cools adiabatically. So instead of cooling as 1 plus Z as the CMB does, it cools as 1 plus Z square because it's a non-relativistic species. So the gas cools further. Okay, so now basically you have the possibility that the spin temperature will no longer stay at the CMB temperature, but might drop down to the gas temperature. So this is the spin temperature evolution. Sorry, this is the CMB temperature evolution, and this is the kinetic temperature evolution. Okay, so let me just first talk about what happens to the kinetic temperature. Now the kinetic temperature, at some point when the first X-ray sources turn on, they will also lead to heating of the gas. Okay, and so you'll get this heating from the first sources. So the kinetic temperature initially follows the CMB, then it cools adiabatically, and then it heats up. Okay. Now to understand the spin temperature, we need to know what the spin temperature is going to couple to. Is it going to couple to the CMB temperature or the kinetic temperature? To understand this, we need to look at those coupling coefficients, X alpha and XC. Okay. So this X alpha and XC is a function of redshift, and one corresponds to what the CMB effective rate is. And when XC is larger, which happens at earlier times, okay, the collisional induced rate is large, and therefore collisional processes determine the spin temperature. And so collisional processes would initially set the spin temperature to the kinetic temperature of the gas. So initially the spin temperature tracks the kinetic temperature. So even when the gas cools, the spin temperature continues to track the cooling gas. Okay, so it continues to drop with the gas. However, at some point, there's a transition where the collisional coupling becomes inefficient and the CMB induced coupling becomes large. And so now the spin temperature heats back up towards the CMB temperature. Then once Lyman-alpha sources turn on, okay, at some low redshift around 20, again, the spin temperature drops towards the gas temperature, and it continues to keep track of the gas temperature as the gas temperature rises. Okay, so the spin temperature has this behavior. Okay, it sort of has one dip where it drops from the CMB temperature down to the kinetic temperature, and then a second dip where it drops back down again to the kinetic temperature and then rises. And these two transitions, okay, this transition away from the gas back to the CMB temperature and back down, are mainly due to the fact that the collisional rate drops below the CMB rate, and then it rises back up again, or it couples back to the gas again, because the Lyman-alpha rate becomes large. Okay, so this prediction of two dips, okay, in the spin temperature is due to these two transitions. Okay, one is where the collisional coupling becomes inefficient, and the second is where Lyman-alpha photons turn on. Okay, so now our measure of intensity, or delta TB, is basically a measure of the deviation between the spin temperature, the CMB temperature, and the spin temperature. So whenever the spin temperature drops below the CMB temperature, you have an absorption signal. Okay, so you have one absorption signal here in the early universe, and you have a second absorption signal here in the late universe at redshift 10 or so. And also remember that the actual absorption signal is a product of the ionization fraction times some measure of the deviation between CMB temperature and the spin temperature. So eventually, once the CMB temperature and once there's no more neutral hydrogen, okay, the signal must go to 0. So this explains the standard cosmological signal. There are two absorption dips corresponding to this dip in the spin temperature and the second dip in the spin temperature. Okay, and you can also understand why you cannot have a very large absorption dip here. This second absorption dip, okay, cannot be very large because there's a limit to how much the gas can actually cool. Okay, because we know when these electron processes become inefficient at keeping the gas in equilibrium with the CMB, and therefore we know exactly how much the gas can cool. It cannot cool faster than adiabatically, and in the standard cosmology, it can only cool adiabatically, which means it's just redshifting away its momentum. Okay, and therefore we know a limit on how strong this absorption dip can be, and it cannot be any stronger than about 150 millikelvin or so, which is much weaker than the 500 millikelvin dip seen by edges. Okay, so if you invert this, instead of looking at redshift, you look at frequency. So frequency increases the other way. Okay, then you get these two absorption dips followed by an emission signal followed by a disappearing signal. So that explains the standard cosmological signal that you see. And if you want to explain the edges absorption dip, you need more absorption somewhere here. Okay, and the way you get this, let me just skip all of this. Okay, the way you get this additional absorption is you need to have some mechanism which allows the gas to cool more significantly than what happens in the standard cosmology. Now, the only way the gas could cool more significantly is if it has another reservoir that it can interact with, which can absorb some of the kinetic energy of the gas. Okay, and that other reservoir has to be colder than the gas itself. And the only thing that we know that is colder than the gas is the dark matter. So people have proposed models where many people have proposed models where the baryons can interact with the dark matter and exchange kinetic energy. And this exchange of kinetic energy allows the gas to cool more significantly. So it starts cooling earlier, let's say, and you still have the same two absorption dips, but the second absorption dip is much stronger, or even the first one is stronger. Okay, and they're much stronger because the gas is much colder. Okay, so the transitions in the CMB rate, in the spin temperature, the transitions in the spin temperature are still due to the same mechanisms. Okay, even in these excess cooling models, they're still due to the same mechanisms. The difference in these excess cooling models is that you allow the gas kinetic temperature to start cooling much earlier through energy exchange with dark matter. Okay, so now let me come to our model and how this differs from the standard cosmology, as well as how it differs from these excess cooling models. So what I'll talk about is this dark matter spin flip interaction model. So in our model, we introduce a new interaction between dark matter and electrons, as I told you, which allows the spin of the electron to flip. So what this does is it allows you a new mechanism to directly flip the spin temperature of neutral hydrogen. Okay, so it's not just due to cooling of the gas, but now you actually have a direct mechanism which allows you to, just like these other processes with CMB excitations and de-excitations, or collisional coupling or Lyman-alpha couplings, this process directly allows you to alter the spin states of hydrogen from the ground state to the excited state or vice versa. Okay, so this would introduce two new rate coefficients, which are the dark matter induced excitation rates and de-excitation rates. And we do this through a new axial vector interaction. So there's an axial vector, okay, which interacts with dark matter through, and it has two coupling constants, g chi and ge. G chi is the coupling of this axial vector to dark matter. Ge is the coupling of this axial vector to electrons. And so this model has 5 parameters. It's g chi and ge, which can be expressed as alpha chi and alpha e. There's the mass of the dark matter candidate, and there is the mass of the mediator, which is V. And there's also F, which is an additional parameter, which we assume, which is the fraction of dark matter, which is made up of this type of particle. Okay, it doesn't have to be all of the dark matter. It can be some small fraction of the dark matter. Now, what this interaction can do is it can induce processes like dark matter interacts with hydrogen in the ground state, converts it to dark matter plus hydrogen in the excited state, or vice versa. Okay, you can have this reverse interaction where the excited state can be de-excited to the ground state. So our model actually has 2 distinct effects. Okay, it can both directly change the spin temperature, okay, through this kind of process, but it can also lead to standard energy transfer. It allows for kinetic energy transfer between dark matter and the gas. Okay, so these excess cooling models that have been proposed to explain the edges signal, they only have this energy transfer. They do not have this direct spin flip mechanism, right? Which can have a much more dramatic effect on the 21 centimeter signal. Okay, one thing that we found, which is really interesting, is that in this model, although you have both these processes, because the same process, okay, the same process is not only flipping the spin, but it's also transferring kinetic energy. But what we found is that, interestingly, there's a hierarchy which indicates that the spin flip rate, okay, is actually much larger than the rate at which you transfer kinetic energy. So that's what leads to distinct predictions of our model as compared to these excess cooling models, in that the spin flip rate is always going to be important, okay, in these in this model, okay. So for those of you who are particle physicists, let me tell you why 21 centimeter physics is actually going to be interesting for testing these kind of dark matter interactions. So the question is, why does dark matter spin flip coupling rates dominate the CMB rate? Okay. Now, of course, if you make these couplings very large, you can always say that this rate is going to be very large. But as I'll show you, even for very weak couplings, this rate can be significant compared to all these other rates that you expect in the standard cosmology. Okay, the reason why this dark matter spin flip rate is large can be thought of in 2 different ways. One is the CMB rate, induced rate for this, the spin flip is really low. Okay, because as I told you, the photon induced transitions are highly forbidden. Okay, there's no direct transition that is allowed from the excited state to the ground state or vice versa. The second reason why the CMB rate is low is because the Rayleigh-Jeans tail of the CMB, where you actually need these photons to exist to have these transitions, the Rayleigh-Jeans tail of the CMB has relatively few photons compared to the peak of the CMB. Okay, so you have relatively fewer photons which can actually induce the spin flip. The second thing is, why is the dark matter rate itself large? Okay, the dark matter rate is large because the axial vector mediator, as opposed to a vector mediator, which is the photon, allows a direct spin flip interaction. Okay, so it's not a forbidden channel, so it's not suppressed by these additional factors. The second thing is that the cross section, it turns out, the cross section for this interaction scales as 1 over the hyperfine splitting square. Okay, at least the Born level amplitude, Born level scattering amplitude scales as 1 over delta square. Well, delta is that small hyperfine splitting. So the cross section is huge, even if the coupling constants are very small. And the third is that the rate is also large for low dark matter masses. Okay, because if the dark matter mass is lower, then you have a larger number of dark matter particles, because we know the total density. And so if you have a larger dark matter number density, and you would also have a larger speed of the dark matter particles for a given temperature, so that also increases the rate of these interactions. So really, this 21 centimeter signal is very similar to intensity frontier experiments in particle physics and terrestrial experiments. And it's because the background, you're talking about a process that is extremely rare, okay? And it's rare in the standard model, and you're looking for a signal on top of that. Okay, so it's an ideal testing ground for new physics. There's a low background rate and there's a high signal rate that you could possibly have. Okay, of course, the challenge is still the foregrounds. Okay, it's the cosmological signal is weak, but it's the galactic foregrounds from which you have to dig out this 21 centimeter signal. That's the real challenge for 21 centimeter experiments. Okay. So let me tell you about two things: how you calculate in this model, how you calculate the spin flip excitation rate, and how you calculate the energy transfer rate. Okay, and I'll tell you why these two rates are large and why the cross-section scales as 1 over delta square. So the effective potential that you can calculate between dark matter and hydrogen. How am I doing on time? How much time do I have? Can I go for another 5 or 10 minutes?
Yeah, I think that's fine. That's fine.
Okay, thanks. Okay, so the effective potential looks like this. It's G chi GE over R times e to the minus mv over R. So far, it looks like a standard Coulomb or Yukawa potential. But there's also this effective operator, which is the SE dot S chi. Okay, so this is the thing that actually couples the spins, okay, and can flip one spin into another. So when you have dark matter interacting with hydrogen, so we assume that the mediator is very light. And so what you would have is if you had an elastic massless mediator, you might expect a cross section with scales like Rutherford scattering. Okay, so it's alpha chi alpha E over mu square V to the 4 sine to the 4 theta by 2. Okay, so this was if the mediator was actually massless. And as is well known, okay, this Rutherford scattering has a singularity at forward scattering. Okay, so when you have forward scattering, these things go right through each other. Okay, and so you have a high probability of that, of forward scattering. Okay, now for standard Rutherford scattering, that forward scattering doesn't really do anything. They just go right through each other. But here, that forward scattering is important because now you can have a transition from the ground state to the excited state. Okay, so you will actually cut off that singularity by the mass splitting between the ground state and this excited state. Okay, so you'll still be dominated by forward scattering, but that singularity will be cut off either by the finite mass of the mediator or by the fact that there's a threshold momentum needed for this reaction to take place. So when you cut off that singularity, the cross section is no longer infinite, okay, but it's rather 4 pi alpha E alpha chi over that delta square, where delta is that hyperfine splitting. Okay, so we're working in the limit where the singularity is mainly cut off, not by the light mediator mass. So the mediator mass is assumed to be extremely small. It's really cut off by the hyperfine splitting between this state and this state. So the cross section is large. Okay, it's 1 over delta square. And the other point is that you have to thermally average this cross section. Okay, and you ask, well, what is the sort of effective temperature? So once you couple to the spin temperature, okay, we know that the spin temperature through this interaction must now couple to a new temperature scale. That new temperature scale is given by the scale T effective, okay, where T effective is found by taking what the relative velocity is a temperature scale of sort of the reduced mass of the dark matter and the hydrogen times some effective velocities, the relative velocity square. And this relative velocity square is this, the expectation value of this is like adding the standard deviation of the dark matter velocity distributions and the variance of the hydrogen velocity distribution. So it's some combination of the kinetic temperature of the gas and the kinetic temperature of the dark matter. Okay, so through these spin flip interactions, you now couple to this new effective temperature scale. So this interaction will induce a coupling to this new effective temperature scale. And similarly, you can also work out the energy transfer rate. But the energy transfer rate is small because, again, most of the scattering is forward. So if you weight the energy, this cross-section by the amount of energy you transfer in these reactions, the typical energy you transfer is only of the order of delta, which is the hyperfine splitting. But the actual energy that you're carrying is of the order of the effective temperature. Okay, so what is called the energy transfer cross-section is much smaller. It's suppressed by this additional factor of delta over T effective. Okay, so therefore the kinetic energy transfer rate is relatively low compared to the spin flip induced rate. Okay, so finally, the expression that we have for our spin temperature is modified from the standard cosmology, and it's also modified from these excess cooling models, because now we have a way to directly flip the spin. So the spin temperature can be, instead of just coupling to the Cmb temperature or the kinetic temperature of the gas, it can couple to this effective temperature scale. And in the limit where the dark matter mass is low, that effective temperature scale is effectively just the dark matter temperature. So through our spin flip interactions, we can directly couple the spin temperature of the hydrogen to the temperature of the dark matter, which can be very, very low. Okay. And in addition to this, of course, you have this energy transfer processes as well. And the energy transfer controls this rate, and it also controls what the effective temperature is. Okay, so again, let me just come directly to what our signal is. So I told you that we have a 5-parameter space model where we have the coupling constants alpha E, alpha chi. It's only the product of those that really matter in this interaction. And there's the mass m chi. The mediator mass is unimportant to the extent that we just assume that it's light. Okay, so as long as it's light enough, the mass of the mediator is unimportant. And the other parameter is F, okay, which is the fraction of dark matter made up of this spin flip dark matter. So we considered various cases of this spin flip type dark matter. So F is 1, where it's all of the dark matter, or smaller fractions of the dark matter. And now the claim is that we are going to get a strong broadband absorption signal in our model. The reason the signal is strong is because now you can couple the spin temperature to a temperature scale which is much smaller than the Cmb temperature, which is the dark matter temperature, which is even smaller than the gas kinetic temperature. So it's really going to couple to a very, very low temperature scale. And it's broadband because this rate xd, the coupling to this dark matter temperature or this effective temperature, is going to be large for most of the cosmological history. For most of the cosmological history, this rate is large. So effectively, the spin temperature is much lower than the Cmb temperature over a large range of redshifts. And therefore, you will have a large absorption signal. Okay, so let me show you. So these are different regions of our parameter space. And we took a benchmark where we're trying to get an absorption signal close to what EDGES has seen at 80 megahertz. But again, we're not trying to explain the shape of the EDGES signal. We're just using this as some kind of benchmark. And we're trying to see how strong an absorption, or what the shape of our absorption signal looks like. Okay, so we have several different regimes depending on whether of parameter space, depending on whether the gas kinetic coupling to the dark matter temperature is important or not. Okay. So if the kinetic coupling is important, then you will also transfer large amounts of energy between the gas and the dark matter. So you have different regions of parameter space here, here, and here, where you can here is where the kinetic energy transfer rate is large at large coupling. And in this weakly coupled regime, even if you don't transfer large amounts of kinetic energy, you can still have spin temperature basically coupling to the dark matter temperature. Okay, so these 3 regimes give you 3 different absorption signals. Okay, so the first one gives you a strong absorption signal like this. The second one looks something more like this. The third one looks something more like this. Okay, the important point is that in all these cases, okay, the signal is strong and it's broadband. It's spread over a large range of frequencies. And again, it's because the spin temperature is now coupling to a new temperature scale. It's not the gas temperature anymore. It's coupling to this much lower temperature scale, which is the dark matter temperature. Okay, so the other interesting thing is the absorption signal before was sort of a tracer of the gas kinetic temperature, in the sense that when you measure it, you're kind of measuring the kinetic temperature of the gas. Now that's no longer the case. When you actually measure the absorption signal, you're not really measuring the temperature of the gas anymore. You're measuring the temperature of the dark matter. Okay, so that's another thing that's interesting about this model. Okay, so I won't go into the details of the constraints, but we consider a large number of constraints, and we show that this model can be safe from these constraints. One of the most important constraints is the constraints are actually on the mediator, rather than directly on the model on the dark matter itself. Okay, because this mediator introduces forces between electrons themselves, so it can lead to short-range spin-dependent forces between electrons on the millimeter to nanometer scale. There are other constraints which you might think would be very important, like collider searches and stellar cooling, but these turn out to be model dependent. So if in extensions of our model, you can avoid stellar cooling constraints, for example, by having this mediator pick up a mass inside stars, and that would prevent stellar cooling constraints from applying. Okay, so if you assume that these constraints do not apply or can be modeled away, right? Then there's a lot of this parameter space which still gives you your strong possible cosmological signals. Okay. However, we find that the cases where the dark matter is made up, 100% of this kind of dark matter will not work. Okay, it has to be 10% or less of the dark matter. And even when it's 10%, it has to be in this weakly coupled regime where there's not much kinetic energy transfer, but there's only spin flip interaction. Okay, and the spin flip interaction is really the novel feature of our work. Okay, so let me just conclude. So again, I want to draw the contrast between the standard cosmology, which is this red curve, or the excess cooling models as needed to explain the edge signal. Our model predicts this strong broadband absorption feature spread across a large range of frequencies. And these future experiments, which are coming online, could actually test this. Okay, and the other interesting thing is, once you actually test this, you are in some sense measuring the temperature of this dark matter. Okay, so our main prediction, to summarize again, is a single strong broadband global 21 centimeter signal. This is unlike anything predicted in the standard cosmology or excess cooling models. It gives an alternative class of templates for signal extraction to people actually doing these experiments to look for a different kind of signal. And it requires different strategies for analysis, because now your signal is not going to be in one waveband. You actually need multiple experiments to corroborate the existence of such a signal. The other predictions that could be interesting, which we haven't explored, one could be the stochastic 21 centimeter signal, that is not looking at the spatially isotropic signal, but those anisotropies that I showed you earlier on. And also, if you could have some kind of independent probe of the gas temperature, which is not, you could see that this absorption signal is not tracing the gas temperature. Okay, and that could be another interesting test. From a particle physics perspective, for theorists, the interesting thing could be to build UV completions. You would have to build a model with broken standard model gauge symmetries to evade collider constraints, because it turns out that simple extensions would be anomalous, okay, of this axial vector interaction. You'd also have to build models that can evade the stellar cooling and extra radiation constraints, okay, because this extra mediator could contribute to delta N effective, the number of effective neutrinos seen in this, which is constrained by the Cmb. Other tests of this model, you could have new collider physics tests where you either produce the mediator directly, or you could have short-range forces between electrons on the millimeter to nanometer scale. So there are these very precise experiments which are trying to measure these kind of spin flip interactions. Okay, thank you very much for your attention, and I'm happy to have any questions, comments, or suggestions.
Yeah, thank you very much, Vikram, for a very informative talk and giving a very nice introduction also. So we have time for some questions. There's one in the chat because Celine had to leave. Maybe I can you comment a little bit more on constraints technically? So she was basically saying that those axial vector couplings have been considered before, and there are a number of constraints, and maybe can you comment there a little bit more?
Okay, so I'm not sure what the paper is that you're referring to.
Yeah, I think that's about structure formation, but I think it's more general about constraints.
Right. So let me just talk about these different constraints. So so let me talk about the ones which are sort of would seem like the obvious ones. Okay. And the model building aspects of those. So the stellar cooling constraint is basically if you have stars and you produce these axial vector mediators inside those stars, they would carry away energy from the center of the star, and you have cooling from white dwarfs and the sun, right, which sets strong constraints on such kind of cooling. Now, this would actually rule out a large region of our parameter space. Though the one thing I'll emphasize is our couplings are still very small. Okay, and the reason the couplings can still be so small and you can have a large spin flip rate is for precisely the reasons that I told you, that it's really dominated by forward scattering. Okay, and because of this forward scattering process, the cross section really scales as 1 over the hyperfine splitting square, and that's why the cross section is huge even for small couplings. But even these small couplings are constrained by stellar constraints. But if you, so people have written models not just for our model, but even other models that try to explain the edges signal, how you can evade these stellar cooling constraints if you have a light mediator. And one of the main ways you evade them is either by introducing a mass for the mediator inside a dense environment. So it's an environmental interaction, and that prevents stellar cooling constraints from applying. The collider constraints are a little different. The collider constraints have to do with when you try to build a UV completion of this model. The UV completions typically are anomalous, and this leads to anomalous decay, decays of the Z boson to a photon plus this axial vector. Okay, so you'd have those kind of decays, and those of course are highly constrained. But if you build a model which violates electroweak symmetry, a UV model which possibly violates electroweak symmetry, then you could potentially get around these collider constraints. Okay, we haven't shown that this could be done. We're not sure if it can be done, but that is a potential route to evade these constraints. So these actually turned out to be the most stringent constraints. We did consider short-range forces on the millimeter to nanometer scale, and something more along the lines of what Celine pointed out, which is cosmological constraints. So one thing that you want is you want kinetic decoupling of to avoid things like structure formation or yeah, okay. So let me say what the kinetic decoupling constraint is. So the specific kinetic decoupling constraint that we considered was the CMB is initially tightly coupled to the baryons, okay? And the baryons, if they're tightly kinetically coupled to the dark matter, then the dark matter is tightly coupled to the CMB. And that is very bad for structure formation because the dark matter needs to be cold for structures to form. Okay, so this kinetic decoupling constraint actually rules out if this is most of the dark matter is in this form. However, if only a small fraction of the dark matter is in this form, basically this kind of dark matter could be hidden in the uncertain. It basically behaves like baryons at early times in terms of its kinetic coupling, but it's small enough that it's within the uncertainty that we have on the baryonic fraction. Okay, so it's like a baryonic component at early times, okay, cosmologically, but it's a small fraction of the dark matter. But that small fraction is enough to give you a large spin flip signal. These are probably the most important constraints. The other constraints maybe I can talk about later, but or you can read the paper. But it's about delta ineffective, and again these are much more easier to evade. Okay, so the collider searches and stellar cooling are the strongest, but model building potentially you can get away from those. These ones are actually the interesting constraints which you can use to rule out certain regions of our parameter space.
Mm-hmm. Yeah, thanks a lot. I think in the interest of time, maybe we can take one more quick question. I have actually a couple one I would like to ask you, just because I've seen that some people already had to leave because of other teaching and so on commitments. Maybe I asked you that one small one. So those, I guess those vector bosons, they are not thermalized, right? Because otherwise you're running in that delta N effective constraint.
Right.
But they're relatively strongly coupled to dark matter. Is that right?
Yes. So we assume that alpha chi is something like 0.1 and alpha E is, I mean, for the spin flip, for the signal that we predict, of course, it's only the product of these that matters. Mm-hmm. But yes, they could be relatively strongly coupled to the dark matter.
I'm wondering whether you could efficiently produce it from dark matter interactions. So it's kind of radiating off the. Okay,
so if you're talking about the delta ineffective constraint, one way you could avoid that is let's say if you assume that this vector boson decays early enough, right? So if it has a small mass, and so you could imagine that it decays to neutrinos, let's say, okay, or it decay, yeah, or photons or something like that, okay. So it can decay to 2 or 3 photons or something like that, okay. So you could have either those kind of decays, and if that decay is early on, right, then the decay products quickly thermalize, right, and therefore you avoid this delta ineffective constraint.
But okay, so you have to then introduce more couplings.
You have to introduce, yeah. So yeah, so the question is, what happens if it's stable? I think I don't know, we've not really worked out the details. I think it would depend on what region of parameter space you're in to work out its abundance. But yes, that would set some constraint.
No, that's good. Yeah, thanks a lot. Thanks a lot, Vikram. So how about the following? We finished the official part.